Hi everybody, and welcome to this video about why the impulse response won't work for subwoofers. I like to think of this video as a complement to Mauricio Ramirez's excellent webinar called Interpreting Delay Finder Data. I strongly encourage those who haven't seen this webinar to do so before continuing. The webinar can be found at the Meyer Sound website. For those who are already familiar with the webinar, let's continue by briefly refreshing our memories. Our dual-channel FFT analyzers transform the incoming measurement and reference waveforms from the time domain into spectra in the frequency domain by means of the fast Fourier transform. When we compare the measurement spectrum with the reference spectrum, we obtain the transfer function in the frequency domain, which shows us the ratio of output over input expressed in decibels, and the difference in time between output and input expressed in degrees. When we apply the inverse Fourier transform to these results, we obtain a second-generation transfer function in the time domain, known as the impulse response, without firing a starter pistol, popping a balloon, or clapping our hands. It's important to emphasize that the impulse response is a transfer function as well, but one in the time domain. It describes the relation between output and input just as accurately, but from a different point of view. One could also say that the transfer function has two phases, one in the frequency domain, the traditional transfer function, and one in the time domain, the impulse response, two different ways of portraying the same identical information. Let's look at various ways of viewing the impulse response for this virtual two-way speaker. Notice the absence of a flat phase response. The phase shift we observe is commonly caused by using minimum phase filters for crossovers and/or loudspeaker protection. Minimum phase filters are called that way because they introduce the least amount of phase shift for a given magnitude response. In the analog domain, the phase shift is caused by using, for example, reactive components such as capacitors and inductors. For capacitors, it makes sense to start by looking at voltage first. From a direct current or DC point of view, the capacitor is an open circuit and no current flows. One plate remains charged until the voltage is eliminated and then it discharges. Through the electrical mechanical analogy, we can study the capacitor's behavior by looking at a spring. The electrical mechanical analogy tells us that mechanical properties like applied force can be expressed as applied voltage in an electrical circuit. Displacement can be expressed as charge, velocity as current, acceleration as the time derivative of current, kinetic friction constant as resistance, and mass as inductance, and finally compliance or reciprocal stiffness as capacitance. Hence the reason that we will look at a spring to understand the properties of a capacitor. If we apply a unidirectional constant amount of force analogous to voltage and compress the spring, the result is a steady state situation. There is no motion, so no velocity, analogous to current, until the force is eliminated and the spring expands. However, if we apply a bidirectional alternating force, there's motion and velocity. At maximum compression or expansion, velocity is zero, telling us that force and velocity, analogous to voltage and current, aren't in phase. Back to the capacitor. From an alternating current or AC point of view, current will flow whenever we alternately charge the plates. When voltage is at a maximum, current is zero. But when the voltage changes from positive to negative or vice versa, current increases. There is a 90-degree difference between the peaks in the chart. Voltage across a capacitor lags current by 90 degrees. Capacitors oppose direct current by raising their impedance and resistance stopping low frequencies and allowing high frequencies to pass. A high-pass filter. Inductors, on the other hand, oppose alternating current. From a DC point of view, an inductor is a straight wire allowing current to pass in a single direction. In the mechanical domain, inductance is analogous to mass. The law of inertia tells us that mass opposes a change in velocity, analogous to current. When current is at a maximum, voltage is zero, but when current changes direction, voltage increases. Again, there is a 90-degree difference between the peaks in the chart. However, voltage across an inductor leads current by 90 degrees. Inductors oppose alternating current by raising their impedance or resistance, stopping high frequencies, and allowing low frequencies to pass. A low-pass filter. Each increase in filter order introduces an additional 90 degrees of phase shift. This is the trade-off for obtaining a given magnitude response with minimum phase filters. The phase shift in our virtual speaker is caused among others by a fourth order crossover at 1 kHz introducing 360 degrees of phase shift, and a fourth order high pass filter for speaker protection at 63 Hz introducing another 360 degrees of phase shift. The linear impulse response can be seen in the top plot of this slide. It shows the ratio between output and input, and there is little to no apparent ringing caused by the phase shift of the filters. The logarithmic view shows the 20 log base 10 conversion of the absolute linear values. Polarity information is lost in this particular view. Apparently, there's more than meets the eye. The tail or decay of the impulse response is considerably longer than the way it appears in the linear view. It extends beyond 20 milliseconds. Then there is the ETC or energy time curve view, which is basically the envelope or contour over the peaks of the logarithmic view. This is especially apparent when we superimpose the ETC plot on top of the logarithmic plot. Subwoofers are band-limited devices spanning 1 to 3 octaves at most. To understand why the impulse response won't work for subwoofers, we need to study the effect of band limiting on the impulse response first. However, if we start band limiting our signals with typical minimum phase filters, we affect both magnitude and time simultaneously. The fourth order Linkwitz-Riley low-pass filter in this slide exhibits a 24 decibel per octave slope, but also introduces 360 degrees of phase shift. So let's look at band limiting exclusively, without introducing the typical phase shift, by resorting to linear phase filters instead. Filters that maintain a linear flat phase response regardless of the magnitude response. Smart runs natively at 48 kHz. So this gives me a full range bandwidth of 24,000 Hz, half of the sample rate. Our analyzers, in contrast to our ears, are linear devices. What looks like minor steps on a logarithmic scale has a great effect on the available data for our analyzers. This is what will happen when I measure a microphone cable at unity gain. 24,000 Hz of information sent away would be returned instantaneously, producing a single sharp spike with a ratio of 1 or 100% on a linear scale, or, like in this instance, 0 decibels on a logarithmic scale. Don't pay attention to the actual numerical values in the center of the time scale of the impulse response in these slides. Just focus on the shape of the impulse response. If we reduce the bandwidth by 50% or 1 octave, lowering the corner frequency from 24 kHz to 12 kHz, we observe a 6 dB drop in the impulse response on a logarithmic scale. If we lower the corner frequency by another octave, we see again a 50% reduction, leaving us with 25% or minus 12 decibels on a logarithmic scale. Lowering the corner frequency again by 1 octave reduces the bandwidth by another 50%, dropping the impulse response by an additional 6 dB. Another 6 dB at 1K5, another 6 dB at 750 Hz, another 6 dB at 375 Hz, another 6 dB at 188 Hz, and finally another 6 dB at 94 Hz. Each bandwidth reduction by an octave results in an additional 6 dB drop of the impulse response. Notice the equal and symmetrical amounts of pre and post ringing, characteristic for linear phase filters, and the widening of the impulse response, indicating low frequency content. By the time we get to 94 Hz, we are left with 1/256th of the initial information, and the amplitude has dropped to minus 48 decibels. There is less than 0.5% of the initial information for the analyzer to work with. One way of offsetting this progression would be by raising the output level by 6 dB for each octave in bandwidth reduction accordingly. But with ultimately 48 decibels of loss to compensate, there is limited merit to this solution. Next, let's study the effect of time on the impulse response exclusively by introducing phase shift without band limiting. For this exercise, I will use all-pass filters at the same corner frequencies, which, like the name suggests, allow all frequencies to pass. Fourth order phase shift introduces half a cycle of group delay at the corner frequency. A group delay implies that a group of frequencies is delayed, whereas another group of frequencies is not. No filter, no phase shift, no group delay. With high corner frequencies, the same constant amount of phase shift, 360 degrees, translates to little group delay for a wide frequency range. However, if the corner frequency drops by 1 octave, group delay increases in exchange for fewer frequencies affected. This is 6K, 3K, 1K5, and now we can see an elevation in the group delay plot for frequencies below 1.5 kHz. 750, 375, 188, and finally 94 Hz. About 5 milliseconds of group delay, but only for a 2-octave wide span. Also notice how the impulse response shows an increase in post ringing exclusively for lower corner frequencies. But the amplitude remains virtually unaffected, because bandwidth is not affected. Let's compare bandwidth, group delay, and the combined result next to each other. The bottom plot is the typical behavior we observe with minimum phase low-pass filters, and its appearance is caused by two phenomena. Band limiting reduces the ratio or amplitude of the impulse response, and phase shift or group delay introduces ringing or oscillation. This is full range, no filtering. This would be 12 kHz, 1 octave down, and we see a 6 dB drop in the amplitude and 0.4 milliseconds of group delay for frequencies below 12K. lowering the filter by another octave, drops the impulse response to minus 12 decibels, and doubles the amount of group delay, but only for frequencies below 6K. Lowering the filter by another octave, drops the impulse response amplitude to minus 18 decibels, and it doubles the group delay again to 0.17 milliseconds for frequencies below 3K. 1K5, 750, 375, 188, and finally 94 Hz, where the amplitude is down to minus 48 decibels, or less than 0.5% on a linear scale. And we have over 5 milliseconds of group delay, but only for frequencies below 94 Hz. Now that we understand how band limiting and phase shift together affect the impulse response, let's look at a virtual but typical subwoofer. The most common subwoofer design, arguably, is the vented or ported enclosure. Through the electrical-mechanical analogy, we can model the mechanical properties of the enclosure like mass, stiffness and friction in an electrical circuit made of resistors, inductors and capacitors. The circuit teaches us that by physically constructing a subwoofer in this manner, it will exhibit fourth-order Butterworth high-pass behavior at the tuning frequency where port and driver resonate, including the accompanying 360 degree of phase shift. However, due to the port, the driver is now allowed to move unrestricted and needs to be protected from physical damage like overexcursion. In the top plot of this slide, we see the phase shift introduced by design. The way the loudspeaker is physically put together. Typically, the speaker is protected from damage by an electrical high-pass filter, again near the tuning frequency. The typology is often Butterworth, because of its low frequency extending capabilities. The Butterworth typology exhibits only 3 decibels of attenuation or half power at the corner frequency. Typically, fourth order is used, introducing another 360 degrees of phase shift at the tuning frequency. So by design and speaker protection, you get 720 degrees or 2 cycles of phase shift at the lower limit of the operational range of the subwoofer, which is currently still full range. And the accumulated group delay up until now is already 32 milliseconds below 32 Hz. In order to turn the loudspeaker into a subwoofer, a low-pass filter is used. Typically fourth order, again introducing 360 degrees of phase shift, but this time at the upper limit of the operational range, introducing 4 milliseconds of group delay for frequencies below 125 Hz. As a result, the entire operational range of a typical subwoofer occurs over a 1080 degree phase span. This is the reason why subwoofers aren't capable of delivering a single frequency at the same time. The subwoofer has become a stretched function of time. They're typically stretched out over dozens of milliseconds, as can be seen in the flashing box. The subwoofer's operational range reduces the amount of information to work with for our linear analyzers to less than 0.5%. And whatever information has survived the process is severely stretched out over time. From my observations in the real world, the delay locator won't be capable of locking into the arrival time of the subwoofer. And if it does, one should wonder which frequency it has found. knowing that the subwoofer won't be capable of delivering all of them simultaneously. That it has become a stretch function of time. In this case, we are synchronized to the highest frequencies, the start of the waveform in the impulse response plot. Again, in this particular example, we're also synchronized to the beginning of the waveform in the impulse response. That is flat phase, that is T0. However, if we move along the impulse response, now the phase trace around 250 Hz has become the flat portion of the phase trace, marking T0. And the frequencies to the right, 250 Hz and up, are leading, and the frequencies to the left, 250 Hz and down, are lagging. If we move further to the right, we see that the frequency response, the phase response around 125 Hz is now the flat portion, and all the frequencies to the right of 125 Hz are leading, and all the frequencies to the left of 125 Hz are lagging. If we move even further, we end up in the center of the passband, and now the phase response at 63 Hz shows a flat response, no elevation, no inclination, and all the frequencies to the right of 63 Hz are leading, and all the frequencies to the left of 63 Hz are lagging. If we move even further towards the lower limit of the operational range, now T0 is 50 Hz, and everybody to the right is leading, and only the frequencies below 50 Hz are lagging. But even here, the linear impulse response hasn't stopped oscillating to the right of this point in time. If the delay locator locks in, it will typically do so to the highest peak, in what barely resembles an impulse. Typically the passband of the subwoofer. But those aren't the frequencies we're trying to align our main speakers to. In a unity crossover, the subwoofers have sole custody in the passband, and they are dominant in level over the main speakers by 10 decibels or more. These aren't the frequencies where time matters because there's isolation. The actual crossover frequency will have arrived earlier than the passband by about 10 milliseconds or so. And it's not a single frequency that we need to align, but an entire range of frequencies of about half an octave wide within the combing zone. The one-time-fits-all frequencies attempt proposed by the delay locator won't work for a signal that is stretched in both directions by 10 milliseconds, if not more. However, in real life, it's very likely the delay locator won't be able to lock on to the subwoofer for several reasons besides the severely compromised data as a result of band limitation. As distance to the subwoofer increases, signal-to-noise ratio will become poorer, to say the least. This can be countered in two ways, by either increasing the number of averages and or increasing the level of the subwoofers and improve signal-to-noise ratio with brute force. Indoors, however, far more challenging is the destructive behavior of low-frequency reflections. Due to their near omnidirectivity, subwoofers, in contrast to directional speakers, aren't capable of avoiding the room. They excite and illuminate the venue with sound maximally, introducing lots of reflections that wreak havoc on both transfer function and impulse response. This would be our virtual subwoofer in an anechoic environment with maximum direct to reverberant ratio. However, if we reduce the direct to reverberant ratio to 20 decibels, we can see some irregularities along the way in the impulse response. And if we reduce the direct to reverberant ratio even further to 10 decibels, we can see even more irregularities in the impulse response caused by late arriving energy. With only 5 decibels of direct to reverberant ratio, we can see that the late arriving energy is starting to become equally large in magnitude to the initial arrival. And at the point in space where direct and reverberant are equally loud, also known as the critical distance, we can see that the late arriving energy is virtually identical in magnitude to the initial arrival. And with subwoofers indoors, this point in space, unfortunately, will be only after a couple of meters, and then reverberation actually takes over. So chances are that at the front of house position, the low frequency energy that we're measuring and trying to locate is predominantly low frequency reverberation and little to no direct sound. I've witnessed situations several times where late arriving reflections produced strong peaks in the impulse response, which the delay locator ended up locking onto. Using the delay locator to determine the arrival time of your subwoofers is a challenging task. If you succeed, the outcome will get you in the ballpark, but so will a tape measure or a laser rangefinder. For the actual alignment, the phase traces and not the impulse response should have the final verdict. Thank you for watching. Until next time.